So here we discuss the signal energy, its power, and power spectral density and energy spectral density. So we'll see that energy spectral density and power spectral density are related to the correlation functions. So first let's see the energy spectral density, which is generally known as ESD. So for that, let's start from the expression for energy. Let's say we have a signal GT. Its energy is denoted as Eg, and we know that it is defined as the area under the magnitude square of GT. So we can also determine the signal energy from its Fourier transform GF through the Parseval's relation. We have discussed this relation before as well. So let's start from on the right hand side. Let's determine the Eg energy from the time domain expression, where it says that we have to consider the magnitude square. So magnitude square mathematically is equal to the GT, the product of GT with its conjugate. So this becomes magnitude square, and after rearranging, so let's consider this G T conjugate. So the this G T can be obtained from its Fourier transform by taking the inverse Fourier transform. So what we have in this bracket is the inverse Fourier transform of GF conjugate. So where you can see e to the power minus j2 pi ft exists, and we have df. So after rearranging or changing the order of integration, we can take out this GF, write it here. This GT can be taken inside. This can be done mathematically. This because GT we have taken it inside, so we bring in DT as well, and DF is written outside. So the term that we have in this bracket gives us the Fourier transform of GF. So this GF can be obtained, it's equal to the Fourier transform of GT. So now in this expression we have GF and its conjugate. So when they are multiplied, so mathematically this becomes GF magnitude square, and we have DF. So we started with this on the left hand side. We started with the time domain expression, and on the right hand side we have obtained the frequency domain expression. Both of them give us the value of Eg, the energy of the signal GT. So if we look at this expression, this gives us the energy now, and it's the integral of GF square, the frequency domain integral. So in other words, it means that this expression gives us the complete bandwidth. We are integrating this term GF square over the complete bandwidth of the signal GT, because we have DF in as the variable of integration, and it's the complete bandwidth because we are considering we are integrating it from minus infinity to plus infinity. So that means whatever is inside this expression, if the overall integral gives us the energy, so that means whatever is inside this expression, that must be energy divided by frequency. So which means that this term GF magnitude square is actually the energy spectral density. It's the energy per unit bandwidth in hertz of the spectral components of GT that are centered at frequency f. So in other words, GF magnitude square is simply the ESD, or the energy spectral density. The unit is per unit bandwidth in hertz of GT. So this is basically the unit of energy divided by the unit of frequency, which is normally hertz. This energy spectral density is defined by denoted by this psi GF, and this is equal to GF magnitude square. So we have discussed the energy spectral density. Now let's see how it is related to the autocorrelation function. So for this, previously we have defined the correlation of GT with itself as it's called autocorrelation function phi g tau, and that is equal to this expression where we have integral from minus infinity to infinity gt and gt plus tau dt. So now our next task is to prove that for a signal gt, its autocorrelation function, which is given by this expression, and its ESD, which is given by this expression, they are related through a Fourier transform pair. So basically, the Fourier transform of energy, the autocorrelation function, will give you the energy spectral density. So this expression we will be proving this expression. So let's look at the basic expression of autocorrelation function, which is this one. If we take the Fourier transform of that autocorrelation function, on both sides we have Fourier transform here, and on the other side, the inside the bracket, the term inside the bracket is the autocorrelation function, the expression for autocorrelation function, as you can see here. We are taking the Fourier transform, so it's e to the power minus j pi f tau. The variable of integration is d tau. After we rearrange it, so we can take out gt and insert this exponential term inside, bring it inside, and the variable d tau. dt is written outside, so the term in the bracket is now a Fourier transform of g tau that is shifted by an amount of t. So due to the shift, we will, by using the time shifting property, we will see that this this term inside the bracket can be written as gf, and due to the time shift, we have e to the power j 2 pi ft. So the exponential term that is multiplied due to time shift appears here. So this, I repeat, this whole expression is the Fourier transform of g tau plus t. So it's a shifted version of g tau. Due to this t, the shift, we will have an exponential term. Rest we will have gf. That comes out because there is no, the variable is now dt. So now if you look at this expression, this is again an expression of Fourier transform of g minus f, because in the expression of Fourier transform we have minus here, that is not there, so that means if we substitute, so this must be a Fourier transform of g minus f, and so we have this product here of gf and g minus f. This is equal to the gf magnitude square. So we know that g minus f and g conjugate f are equal, so conjugate multiplied by the actual gf gives us the magnitude squared. So we started from the left hand side, we have the Fourier transform of autocorrelation function, and on the right we have the energy spectral density. This expression we know is for energy spectral density, which is denoted by this psi g. The italic one is for the autocorrelation function, and the non-italic is for the energy spectral density. So until now we have first proved that this term is the energy spectral density, and so the next thing we've proved is that Fourier transform of autocorrelation function gives us the energy spectral density. So similarly, there is another method by which we can prove the same expression. So let's look at the signal, the expression here. This is for, again, this is for autocorrelation function. We know it is related to the convolution by this expression. So this is the convolution expression, g tau convolution with g minus tau. So if we substitute the values in the formula for convolution, we will see that this becomes, the expression becomes equal to this. So we will have gt, because of the minus tau, we will have gt plus tau here, right? So in this expression, so we will substitute, we'll replace this tau with t plus tau, and when we replace this tau with t plus tau, we are left with gt only. So that this means that the autocorrelation function is the convolution of g tau and g minus tau. So this can be simply proved by substituting values in the expression for convolution. Now if we take Fourier transform on both sides, the Fourier transform of psi g tau is this term, the which we call the energy spectral density. Now, is this actually equal to gf square? So we can see if we have the convolution in time domain, we will have multiplication in the frequency domain. So in the frequency domain, we have multiplication of their Fourier transforms. So the Fourier transform of g t tau is gf. Fourier transform of g minus tau is also gf. So in that means it's g minus f. So that means if we multiply those two Fourier transforms, we get gf magnitude square. So this is another method of proving that the Fourier transform of autocorrelation function is equal to the energy spectral density. So this is one part, and then we have how does this energy spectral density behave in the presence of a system. So let's say xt and yt are the input and the corresponding output of a linear time invariant system. So we are considering an LTI system here. So then we know this expression exists. The output yf is equal to hf. This is the system function of this LTI system multiplied with xf. So if we take squares, magnitudes and squares on both sides, we get this expression. From previous discussion, we know that this is the energy spectral density of y t, and this is the energy spectral density of xt. So we can replace that. In other words, we know that the energy spectral density is denoted by these expressions psi y and psi x. So from this we can conclude that the output signal est, which is this one, is hf square, hf magnitude square times the input signal est. So this is just to prove the relation between the input ESD and output ESD in the presence of a system having system function HF. Now this was energy spectral density. Next is the power spectral density. So as you can imagine, there is a contribution of time in this case. So let's see what are first let's look at the power signal. So for power signal, a meaningful measure of its size is its power, which is the time average of the signal energy averaged over an infinite time interval. So power signal is power of a signal. Let's say if it's defined by pg, it's denoted as pg. So we have a real valued signal gt. So the power would be given by this expression where we have gt square, and the integral is now over one time period, tau minus t by 2 to t by 2. And in this case the time is very large, the time period is very large. So now to determine the power spectral density, we define a signal which is a truncated signal gt, and it's related to gt. So we have g capital T, it's related to gt through this expression. It's equal to gt when within this limit minus t by 2 to t by 2, within these limits, and outside these limits it's equal to 0, right? As you can see, for time t greater than t by 2, it's equal to 0. So this can be visualized by an example plot. This is gt, the time is minus t by 2 to t by 2. This is the truncated version gt capital T, right? So within these limits both of them are equal. Outside these limits, the gt, this one is the truncated one, is 0. So from this, since the signal is finite, this one, so we can find out its energy. The energy would be energy of g t. The truncated one is represented by energy gt, right? So we can see that the power of this signal, the g, because power of gt requires only the interval minus t by 2 to t by 2, and our truncated signal is also present in this interval, and it has the same value within this interval. So that means the power of this signal pg is equal to energy of the truncated signal divided by the total time period, which is from minus t by 2 to t by 2. So as t increases, this value remains the same, because as this t increases, this one, the numerator also increases, the energy also increases. So this ratio remains the same, and the power of the signal remains the same. So if the signal gt is a power signal, then its power is finite, right? And the truncated signal gt is an energy signal as long as t is finite. So since, as we said before, this is within a certain limits, so it's an energy signal. So for this signal, energy exists. For this signal, the actual signal, only the power exists, right? So if the Fourier transform of this truncated is GTF, then from Parseval's relation we know that the energy is equal to, we can find it through the time domain expression by using this expression, or we can find it in the frequency domain by considering this expression, where we now have the integral with respect to frequency. So hence Pg, the power of Gt, is given by, as we saw in the previous slide here, the power of this Pg is given by the energy of the truncated signal, the time average of the energy of the truncated signal. Now when we substitute this EGT from this expression, we get this expression where the term in the bracket represents the energy of the truncated signal. Now again, as T increases, this T increases, this energy spectral density also increases, this one, and so the right hand side of the above equation converges. So overall this result will give us a finite value, because as this t increases, as this t approaches to infinity, this term also increases accordingly, and the ratio, the overall value, is still converges, it's a finite value. So until this point we have proved that the power of the signal gt is related to the energy spectral density of the truncated signal through this expression. So the term in the bracket is the total energy of the truncated signal, and when we divide it by the time t, time interval t, it gives us the power of the signal gt. Now the convergence permits us to interchange the order of the limiting process and integration. So since this is a finite value, we can change the order of integration. So the term with the limit goes inside the integral, just like this. And so this is the new expression which is extracted from this previous expression. If we look at this expression, what do we get is we have an integral of this term with respect to, the integral is with respect to frequency. So in a way, frequency is being multiplied with this term to get power. So that means this term within the integral must be power spectral density, PSD, which is denoted as SGF. So this is exactly what we have done in the next expression. This is the power spectral density. When it is multiplied with the frequency, we get the total power. Right, so finally we have proved the expression for power spectral density, but integrating it with respect to frequency gives us the total power. If it's a symmetric signal, we can integrate it from 0 to infinity, and the power would in that case be twice because of the negative terms being removed. Observe that the PSD is the time average of ESD of GT. So from here, this is the power spectral density. It's the time average of the energy spectral density. So this is the energy spectral density. We divide it by time to get the power spectral density. So this is how the energy spectral density and PSD, the power spectral density, are related. So previously we proved that for ESD, we proved that the Fourier transform of the energy Fourier transform of autocorrelation function, this one, is equal to ESD. So now we will prove that the Fourier transform of time autocorrelation function is equal to PSD. right? For this proof has been shown here. So for a real signal, the autocorrelation function, we know it's equal to this term gt into gt plus tau, right? So this is we have studied this, we have seen this in the video related to correlation functions. The time autocorrelation function of this can be extracted from this expression, where, as you know, as we can imagine, that we would be including time now. It's a time average sort of function. So the time autocorrelation function is denoted by rg, and this rg of a real power signal gt is defined as through this expression. So within a certain limit minus t by 2 to t by 2 we determine, and we have 1 by t outside, so we determine the autocorrelation, and that because of this time average, this same autocorrelation is now called time autocorrelation, right? So now we consider the same truncated signal gt that was mentioned earlier. So we know it's equal to the actual signal gt within this interval, it's equal, and outside this interval it's equal to 0. So from the previous three equations, the time autocorrelation function may also be written as this expression. So which three equations are we talking about? So this is the time autocorrelation function. We substitute the values of this gt here, because uh, this only, the time autocorrelation function only requires this interval. Within this interval, gt and this truncated version of gt are equal. So we can replace these expressions, and this is what we get when we replace those equations. From this part only, when we remove the time part, which is this one, when we remove the time average, we are left with the normal, the autocorrelation function, which has been shown here. So we have phi gt. So the term, this term is only the autocorrelation function, which was shown here. And when we have divided it with the time t, where time t approaches to infinity. So if we look at this expression, this is the autocorrelation function. The Fourier transform of this autocorrelation function, we know from previous knowledge, is equal to the ESD. So the Fourier transform of the time autocorrelation function, which is this, is equal to, if we apply Fourier transform on both sides of this expression here, so this is the RGT, its Fourier transform over here. That means we are going to have limit t approach to infinity as before. We have the time t here as well, and the Fourier transform of autocorrelation function, this one, is equal to energy spectral density, which is written here. So that means the Fourier transform of time autocorrelation function is equal to the PSD, the power spectral density. So in summary, Fourier transform of simple autocorrelation function, which is this one, is equal to ESD, and the Fourier transform of time autocorrelation function, which is this one, is equal to PSD, which is over here, right? So these are the two energy spectral densities and their relation to the correlation functions. So finally, we see signal power and mean square values. How are they defined? So we mentioned that power of a signal is equal to this gt square and integrated over one time interval. This expression shows that the signal power is the time average or mean of its squared value. So to differentiate this time mean from statistical mean, we will denote time mean square values using wavy bar. So whenever you see this wavy bar, that means it is representing time mean square. So that means if we substitute, if we relate this to pg, this power, total power, is the time, and this g square t mean, time mean of the power is equal to time approaching to infinity integral of g square t. So this is the power of the signal, and since it's a time mean, if we take the square root of this, it becomes root mean, right? So that would be under root of this Pg gives us the root mean square of Gt. Right, so we have, in summary, we have discussed the energy spectral density. We derived its expression from the equation of energy, and then we showed that ESD, energy spectral density, is related to the autocorrelation function through Fourier transform. Then we discussed signal power and its power spectral density, and we showed that this PSD is related to the time autocorrelation function through Fourier transform.